Test. 1, 2, 3. Hi, welcome to this week's Recitation. Today we will discuss the exercise in section 2.4. First, let's suppose a f of t plus b g of t equals 0 for all real t. Then we choose t1 to be 0 and t2 equals pi over 2. Then we have, first we substitute t1 in this equation. It gives us a times 0 plus b times 1 equals 0. And we substitute t2 into this equation. So we have a times 1 plus b times 0 is 0. So it gives us a, b are both 0. So we can conclude that f and g the set that contains f and g is linearly dependent. Let's go to exercise 4. First, we recall that cosine 2t equals cosine t squared minus sine t squared, and it is 1 minus sine t squared minus sine t squared equals 1 minus 2 sine t squared. So we have minus f of t plus g of t plus 2h of t is 0 for all t in R. Therefore, FGH, this set, is linearly dependent. Okay, for this exercise, the answer is no. The set of these three matrices is linear dependent. To find the relation of those matrices, you can use the same method in example 11 in the textbook. You can seek how to find the linear relation of these three matrices by reviewing example 11. Okay, first we find the relation between these three vectors. So it gives us 3u minus 5v equals w. So we know that w is in the span of u and v. So by the previous exercises, we have span of w is inside of span of u and v. Since span w is inside span of u and v, so we have the intersection of span u and v and span w is span w. Why? Since if you have two sets and A is inside of B, then the reunion of A and B is the intersection of A and B is A, and the union of A and B is B. So it gives us this is equal to uv, span of u and v. In the future quizzes, if you are asked to show that a set is not a vector space, you don't need to list out all the failed axioms. You only need to provide one axiom that is not fulfilled. Then you can conclude that it is not a vector space. So for this case, apparently not all vectors remain the same if they are multiplied by a unit scalar. Since 1 multiplied with x is not equals x for all x in R. For the first part, first we let P of t equals a t cubed plus bt squared plus ct plus d, where a, b, c, d are real numbers. Then first we differentiate p, so we have 3at squared plus 2bt plus c, and differentiate this, we have plus 2b, and this equals to 24at squared plus 10bt plus 2c. We can see that if L of P of t is 0 for OT, the only condition is that A, B, C all need to be 0. So if and only if A, B, and C are all 0, therefore the kernel of L is real numbers. So if L of P is 0 for OT, the only possible solution is P is a constant. Okay, this one is an easy one. You just need to find the linear relations. Since 3p1 of t minus 2p2 of t plus p3 of t is 0. So they are not linearly independent. In these exercises, we will try to use vectors with exactly 2 entries we will use vectors with exactly 2 0 entries to construct standard vectors in R4. So first we construct this set. And this gives us 1 0 0 0. And similarly, and it gives us 0 1 0 0. And this gives us the 4th standard vectors. And with that, S be the set that contains all the vectors with exactly 2 0 entries. There are exact 2 0 entries in V. Now we have, since T is inside span of S, so span of T, apparently span of T is R4. Since T contains 4 standard vectors. Now, since T is inside span of S, so span of T is inside span of S. And from previous exercises, we know that this is actually equals span of S. And trivially, span of S is inside R4. Now we have span of S is inside R4, and R4 is inside span of S. So we have span of S is R4. This exercise is similar to exercise 3, so we will not do it here. For this exercise, the answer is no, since every function subtract itself is a zero function, so which is continuous. So if we let f of x be a discontinuous function, defined on -1 to 1, then we can see that f minus f is 0, which is continuous. So discontinuous functions is not a vector space. Okay, this one is similar to example 17 in the textbook. So please check it by yourself. In some previous exercises, for simplicity, we assume that the sets are finite, but from now, you should consider that a set might be infinite. So in this exercise, you cannot assume that G equals G1 equals G1, G2, Gn. You cannot do that. So if you do that, you only consider the finite case. So if you want to consider the sets might be infinite, then you cannot enumerate the elements of a set like this. So we know that the vector space BV for part A, we suppose that G is linearly dependent. Since we assume G is linearly dependent, so there exists G1, G2, Gn in G such that there exists a non-trivial relations of G1 to Gn. A1, G1 plus A2, G2 plus, and so on, is 0. Since G is inside H, so G1 to Gm is also inside H. Then it gives us H is also linearly dependent. it means H is linearly dependent. And which is a contradiction. Now for part B. Since H is a subset of V, is a subset of V, we have span of H is inside V. We can conclude that it's because V is a vector space. If V is not a vector space, it's not generally right. Since G is inside of H, we have V equals span of G, and it is inside span of H. So we can conclude that span of H is equal to G. Span of H equals V. Yes. For part 6, here we give an example. We let G be one, 0, 0, 1, and H be and part D, we let the vector space be V, let V be R3. So if we let G equals 1, 0, 0, 0, 1, 0, and we let H equals then H, span of H is V, but span of G is not V. Now let's go to exercise 28. Here we will show that axiom 2 and 3 and this new axiom can imply each other. First, we start from this direction. U plus V plus W. Then by axiom 2, we can exchange these two terms. So we have V plus U plus W. equals axiom 2. Then by axiom 3, we can do this addition first. So we have then so if we have axiom 2 and 3, then we can imply this equation. How about use this equation to get axiom 2 and 3? For this direction, we first show that we can use this equation to have axiom 2. We start from u plus v. Then with the add with other axioms by axiom 4. Any vectors is equal to itself if it is added by 0 vectors. So then by these equations, we can take these out. And again, by axiom 4, any vectors plus any vectors add 0 vectors is still itself. So by axiom 4, so we have u plus v equals v plus u. Remind you that the axiom I'm talking about here is the axioms listed in the textbook, not the axioms listed in the lecture note. They are the same, just the description are a little different. So if you basically the axioms listed in the lecture note is just some combinations of the 10 axioms in the textbook. Okay, now we show that this equation can give us axiom 3 in the textbook. Now let's start from u plus v plus w. Then, since we have shown that this equation can imply axiom 2, so we can use axiom 2 here. Then, by axiom 2, we can exchange these two terms. This will become u plus v plus u plus w. Then again, by this equation, we take this out. So it becomes u plus w. So these new axioms can give us axiom 2 and axiom 3. So these two axioms is equivalent to this new axiom. Okay, this exercise is similar to the proof in Theorem 10. So please read it by yourself. For this exercise, the answer is no. Actually, you cannot use other axioms to create the additive inverse. You can have a set with two binary operations that fulfills all other axioms, but not all non-zero vector. But no non-zero elements have an additive inverse. Here we provide an example. We let V contains only two elements, 0 and 1. Now, the vector addition will be defined as logical OR. Define vector addition as logical OR. For OR binary operations, say A or B is equal to 0 if both of A and B are 0, and A or B is equal to 1 if one of A and B is 1. And we define the vector multiplication as this. Now we need to show that it fulfills all the axioms but axiom 5. Since it takes some time, we will not do it here. So please check that by yourself. Please show that it fulfills. All the axioms. But axiom 5. Please use your own time to check that. Now for exercise 31, 32, and 35, you need to check all the axioms of vector space to make sure they are vector spaces. It's not difficult, so we will leave them to you. Okay, first we will show that span of S plus span of T is inside span of the union of S and T. We let X be an element of span of S plus span of T. Then there exists an S in span of capital S and a little t in span of capital T, such that X equals S plus T. Since little s is inside the span of capital S, so there exists some S1, S2, and so on, Sn in S, such that we can express this little s by these elements in capital S. similarly, since little t is also inside the span of capital T, so we can also express little t by the elements of capital T. Similarly, there exists T1, T2, Tn inside of T such that little t is E1 T1 plus B2 T2 plus plus Bn Tn. Now since x equals s plus t, so it's obvious that s is inside therefore it's inside span of the intersection, the union of s and t. So we can conclude that span of s plus span of t is inside of span of the union of x and t. Now, for the other direction, we leave it to you. So we leave this part to you. So please try it by yourself. For the first part of these exercises, actually the statement is wrong. If we consider S be the set with only zero vector, then there is no such V. That S be this set. So if S contains only zero vectors, then there is no such V. Two. Actually, this part is also no. We can consider this S. If we let S contains 1 0, 0 1, and 1 1. We can see that if we take these vectors out, then the span of S is still R2. If we take this out, the span of S is still R2. But if we take both of them out, the span of S will be smaller than R2. Span of Okay, this exercise is actually pretty similar to an example in the textbook. So we will still draw it here. First, we let S is the set of polynomials. and S is a finite set. Where Pi equals a polynomial of T to degree of Pi, and Pi is a non-zero polynomial. So P1, P2 to Pn are not all zeros. Or none of them are zeros. And we order them by their orders. So degree of P1 is less than degree of P2, and so on. Now, we suppose that S is linearly dependent. Linearly dependent. Then there exists A1, A2, the AN, such that P is equal to the linear combination of P1 to Pn. A1 P1 plus A2 P2 plus AN Pn is 0 for all T. And not all AI is 0. Okay, now that AK be the last non-zero terms in A1 to A1 to AN. AK be the last non-zero coefficient. Then if we call this P, the degree of P, then degree of P is equal to degree of PK, which has at most degree of PK root. but we suppose that it is E0 for OT for all real t. So this is a contradiction. For exercise 46, you just need to use theorem 7 in the textbook. And for the rows, just take the transpose. Consider A transpose and use theorem 7 in the textbook. For the first part of this exercise, of course, Rn is not a subset of Rm, since the elements of Rn are vectors with n tuples, while the elements of Rm are vectors with m tuples. So the first part is no. And for the second part, this one is a very easy one. As long as n is less than or equal to m, then Pm is a subset of Pm. So as long as n is less than or equal to m. Now for exercise 49. A vector space is defined with a set and two algebraic operations. It will not be a vector space if any one of these is not defined, since there is no algebraic operation defined, so it is not a vector space. For part A, no. If you multiply any vectors with a complex number, then the elements of these vectors will become complex number. So for this case, I0 is not in R2. Where? Oh, thank you. And for this part, yes, and it's very similar to exercise 35, so you can review that exercise. It is similar to exercise 35. So we're kind of done here. Is there any questions on the comments section? Okay, then remind you that we have a quiz on Wednesday, and all of you are required to take the quiz in person. And please follow the sitting plan we posted on EE class. Then that's this week's recitation. I will see you next week.